Today we have the paper Along the Timeline Traced Embedding for Temporal Knowledge Graph Completion. And we are very happy that we have Fuwei Zhang, who will present it. And Fuwei is a PhD student from the Institute of Artificial Intelligence at Beihang University. His research interests include data mining, applied machine learning, with a special focus on the representation and application of knowledge graphs. So yeah, we're very happy to have you, and thank you for presenting.
So I can begin?
Yes.
Oh, okay. Hello, everyone. It's my pleasure to participate in this temporal graph reading group. And my name is Zhang Fuwei. I'm the first author of this paper, and I'm now a PhD student in Beihang University. And today I want to share our paper, which is published in CIKM 2020-22. The title of our paper is Along the Timeline Trace Embedding for Temporal Knowledge Graph Completion. And I will introduce our work in 4 sections, including introduction, methodology, experiment, and conclusion. And first, before introduce our paper, I will introduce 2 settings in temporal knowledge graph reasoning, extrapolation and the interpolation. The interpolation is used to fill in missing facts for an incomplete temporal knowledge graph. It helps to supplement missing quadruples across various times. And the extrapolation on the other hand, learns from specific historical information to predict the potential future facts. And both of them can be unified into a link prediction task, which involves predicting entities and relations. For example, in the right part of this slide, we can predict the tailed entity or the head entity, and we can predict the relation between the head and tailed entities. And all this prediction is in a specific time step. And in our paper, we are tackling the job of reasoning with temporal knowledge graph, especially in an interpolation setting. And here's an example. There are some facts about Obama and countries like India. And we are trying to fill in the missing facts by adding missing relations between these entities. And the time range can be chosen from all the times that in the data set, such as we can predict the missing fact in the tau subscript 1 and the tau subscript 2 and the tau subscript 3 and so on. So we call it the temporal knowledge graph completion. Here's our motivation. And existing models, like those using the time translation or rotations, have some limits. They have difficulty to distinguish entities or relations at different time steps. To better capture the representation of temporal knowledge graph, we thought about adding a timeline concept. To tackle this, we aim to distinguish entities or relations at the same time step, and also to distinguish the same entity or relation at different time steps. Thus, we come up with a way to model entities and relations on a timeline. So we propose a timeline trace knowledge graph embedding model for TKG completion, and which aims to embed the temporal entities or relations with a semantic part related to entity or relation, and a temporal part related to the time information. And the right part of figure shows an illustrative example of the embedding distribution of the proposed model. Our model can well distinguish not only different entities or relations in the same time step, but also the same entity in different time steps, such as the day 1, day 2, day 3, and day 4. To be more specific, by modeling different entities or relations on separate timelines, we can see these benefits. The first is that the entities or relations at different time steps have different representation. And in the same time, in one time step, the entities and relations are in the same space of the time step. such as the bottom figure. In the time step 1, every phase, all the phases can build into can construct a steady knowledge graph, and in different time steps, these phases are separated by the timeline. So here we highlight our contributions. First, we propose a novel timeline-based knowledge graph embedding method for temporal knowledge graph completion, which aims to embed the temporal entities and relations considering both the independence and the connections of the semantic and temporal information. And second, TLT-KGE is equipped with 2 actual components, a shell time window module and a relation time step composition module to strengthen the representations of entities and relations. And third, we verified the effectiveness of the proposed TLT-KGE on 3 widely used benchmarks, and the results exhibit our model can achieve substantial improvement over state-of-the-art baselines. And then I will introduce our method. At first, I want to give some definition about quaternion. A quaternion queue consists of a real component and 3 imaginary components, such as this I, J, and K. Like the complex number system, the quaternion number system has a rule of Hamilton product, and the Hamilton product of 2 quaternion is composed of the multiplication of every factor and follows the distribution law in the quaternion. In this product, each part of 2 quaternions make interactions by themselves. For example, A subscript 1 can make the interaction with A subscript 2 and B subscript 2 and C subscript 2 and D the subscript 2 respectively. So in the quaternion space, the Hamilton product can provide more interactions for these embeddings. And here is a simple comparison between the static KGs and static knowledge graphs and temporal knowledge graphs. Comparing with the static knowledge graph, a temporal knowledge graph is composed of many quadruples, which contain 4 items named head entity, also called subject, prediction, the relation, and the tailed entity, object, and the timestamp. And each temporal knowledge graph in a specific timestamp can be regarded as a temporal snapshot. That is to say, in every timestamp, we can construct a temporal snapshot, which can be regarded as the static knowledge graphs. Based on the complex and quaternion number space, and we propose 2 variants of our model. The semantic part represents the information of entities and relations, while the temporal part represents the information of time steps. On the left is in the complex space TLT-KG complex. The model can extend the semantic information from the real axis to temporal axis. That's the real part of the complex number we can represent as the semantic part, and the imaginary axis we can regard it as a temporal part. And for the right part in the quaternion space, TLT-KG quaternion, the model extends the semantic information from real part and imaginary part I to the temporal information, which consists of imaginary part J and K. For the real part and the imaginary part I, we can regard it as the semantic part. And for the imaginary part J and K, we can regard it as the temporal part. So here is the detail of how we combine the semantic and temporal part. In complex space, we can make the whole embedding with semantic and temporal parts by regarding the entities or relations as real part and the timestamps as imaginary part, such as the purple and the yellow The purple is the semantic part, and the yellow part is also called the temporal part. As for quaternion space, we can regard the entities or relations as the real part and the first imaginary part, and the time step as the imaginary parts j and k, and the dimension size of entities, relations, and time steps is the same, are the same. Then we can use the whole embedding to calculate the scores with the help of the rules of complex number system or quaternion number systems. For example, in complex space, we utilize both the score of real part and imaginary part, and the scored function provide different interactions of the embeddings of entities, relations, and time steps. In the quaternion space, the interaction between the semantic part and the temporal part are more complex. And we also provide two additional modules according to the future time steps. The first one is shared time window module, which can strengthen the connections of facts in a range of time. To realize this, we use a shared embedding for those time steps which are in a time range, in the same time range. And the second one is relation time step composition. This is because the relation embeddings are crucial in the temporal knowledge graph computation, since each relation is related to multiple facts in kg. To enhance the expression of a relation at specific time, we introduce this operation to combine both the semantic information and the temporal information with element-wise product. If we want to apply them in our model, we only replacing the related embeddings with our new embeddings. Okay. That we only replace such as the time embedding in the previous embeddings, or the relation embedding in the previous embedding. Following the previous words, and we utilize the L subscript 3 normalization terms for entities and relations. And the temporal embeddings of time sets are supposed to gradually change over time for learning better representation. For example, the embedding from adjacent time sets should be closed. So we utilize a regularization terms for timestamps. And finally, we use the multi-class log loss function to train our model, and we add the different ways for different regularization terms. So in order to prove...
Sorry, just before you go to the experiment, there's a question in the chat if you can take a look in.
Okay.
Yeah, I can also just state it. So you're making it so that the time representation is part of the embedding of the entity. And I'm wondering, like in a transformer, you might have this kind of temporal encoding that is separate, and then you add it to the token embeddings. And I'm wondering if there's a reason that that doesn't capture the sorts of relationships you're trying to model here, or like what motivates the choice to do something more complex like this as opposed to just adding a temporal encoding?
Did you mean the difference between the previous verse and our work?
No, I'm saying in transformers, they break these kind of symmetries that you don't want by adding encodings like positional encodings or temporal encodings. And they're kind of a separate thing that you learn and add to the representations of the tokens. In this knowledge graph thing, you could conceivably do the same thing where you have, your entity embeddings and your relationship embeddings, and then add to them these learned temporal encodings. And it would make, you wouldn't have all this complex mathematics. So my question is, are there additional benefits you get in terms of what you're able to represent by using these other spaces with imaginary components and so on? What's motivating the choice of this?
Actually, we validate the performance in our experiment, and can you pardon your problem?
Let me ask it a different way. Is there a special set of mathematical properties that these vector spaces have that are motivating the choice of trying them out? Or are you just, how did you come to the choice to use these sorts of vector spaces?
I use the such as a quaternion space because inspire the timeline solver. And if we want to build a embedding such as along the time, we use for example, we use the compressed space. We can divide the two axes to two parts. So all the entities can distribution along the time, such as in the time step 1, we have the different entities in this line, and in the time step 2, we have a different representation of entity and the relations. So for the mathematical improvement, I think the first is our model can represent the different, such as the entities in different time steps. So the entity or relations in different time steps have a unique representation. And the second, the entities in the same time step, we can regard it as the such steady knowledge graph. So in the quaternion space, if the entities or relations in the same time steps, so we can remove the temporal part of them, and then it is the semantic part is we can regard it in the compressed space. So such as the modeling different relation patterns, such as inverse or composition, the relation patterns, we can use the compressed. So if we remove the temporal part, then the semantic part is a steady compressed model in the steady knowledge graph. So it has some features.
So is it fair to say this approach has a lot more modeling capacity, something like that?
Can you? I'm not very understand your problem.
That's okay. I think I understand. Thank you.
Okay. So in order to prove the adaptive ability of TLT-KGE in modeling sparse and dense TKGs, we evaluate our model on 3 popular benchmarks for TKG completion, including ICWS-14, ICWS 5 to 15, and GDELT. The first 2 datasets are 2 subsampling datasets from the Integrated Complete Early Warning System, ICWS, and the latter GDELT is a dense KG, which is a subset of a large knowledge graph named Global Database of Events, Language, and Time. ICWS 14 and ICWS 5 to 15 are 2 sparse datasets, while GDELT is a dense dataset with about 3 million quadruples. And this table shows the results of our model. We can find that TLT-KGE outperformed all the state-of-the-art competitors, demonstrating the effectiveness of our model and indicating that our model is suitable for datasets with different sparsity. And we found in the quaternion space, our model performs better than the TLT-KG in the compressed space. Particularly, TLT-KG quaternion achieve better MR score than TLT-KG compressed on ICWS 14 by 17. The results indicate that the interactions in the quaternion vector space more powerful for representing entities and relations with time steps. And we also found that our model achieved greater performance gains on the two sparse datasets in ICWS 14 and ICWS 5 to 15. Specifically, the TLT-KG quaternion outperformed the best baseline on 3 datasets. The results show that our way of modeling semantic information and temporal information can overcome the problem of data sparseness to a certain extent. And we also do some experiments under the bounded parameter setting. The result demonstrate that TLT-KG can model the time evolution on sparse datasets. For the dense datasets, our model can also perform well. However, on GDAL datasets, owing to the small dimension size, many models suffers from the underfitting. Thus, choosing a large dimension size to do the TKG complete task is on GDAL is better. So in order to obtain the influence of 2 additional modules, we do some ablation studies and the results are shown as this table. The proposed model outperforms the variance without relation timestamp composition module and the shell time window module, which shows that both 2 modules have a significant impact on TLT-KG compressed and TLT-KG quaternion, demonstrating that the additional desired modules have a positive influence on temporal knowledge graph computation tasks. So TLT-KG without both 2 additional modules also achieve the state-of-the-art results on ICWS 14 and ICWS 5 to 15 datasets, and also achieve comparable results on GDAL. This phenomenon again verifies the effectiveness of our way in modeling temporal entities and relations. What's more, we also give some visualization of the entity embeddings and relation embeddings compared with other models. The baseline models tend to embed the same entity or relation in different time steps into a cluster. Such results make it difficult for the baseline models to distinguish the representations of entities or relations at different time steps, while our model can easily do so, which validates the efficiency of our methodology. Besides, we also test the model's ability to discriminate between different entities or relations at the same time steps. Table 7, this table shows the results, and we can observe that only on January 1st, the average entity or relation distance in TLT-KG quaternion is larger than in the baseline models, which demonstrate our model can also better distinguish entities or relations at the same time steps. And finally, here is our contribution or conclusions. First, we present a novel model TLT-KG for temporal knowledge graph computation, which regards the time information as a timeline. TLT-KG embeds both entities and relations at different times with a semantic part from the static knowledge graph and a temporal part from the time information. And our model is qualified to model temporal evolution over the timeline with 2 independent paths. Additionally, the proposed methods also introduce the shell time window and the relation time step composition module to enhance the ability of representation learning. And we do extensive experiments on benchmark datasets and validate the effectiveness of our model. So that's all. Thank you. And
Thanks a lot for the great presentation. If there's any question, please feel free to ask.
Thanks a lot. I have a question. Can you go please to slide number 20?
Number 20.
Yes.
This
Yes, please. Can you please explain on the figure where do we see that time? So I do not understand the figures, I think.
okay. For example, on the left part, we
Mhm.
present the entity embedding in the with the TSNE method. So the the previous model D simple E can model the different entities such as the color, the color from the bottom to the top, it represent a different time step, such
Ah,
as okay, the
I
bottom is
understand.
the one time step one, and the top is the time step 300. So this model can model this method can model the entities at different time steps, such as this entity these entities at different time steps is near, such as a line. That our model can represent the entities such as in the lower in the nearly time steps, we can get the same representation like the D sample E, but for the times that larger than the the with the large time steps, we have the different distributions compared with the D sample E. For example, the time step 300, we have far away from the time step 1 to time step 5. So we have the ability to distinguish the entities of different time steps. It is also the same as the relations. In our model, the relations from time step 1 to time step 5 are is more close than the relations in the time step 300. So we have a better distribution. So
Thank you for explaining.
Just one other question. The time that you consider here, is it a continuous time or is it more like a snapshot based?
can you?
It's more like that because you mentioned that the time here, it is shown as the intensity of the colors. So I was wondering whether you consider the time, what is the granularity of the time that you consider?
So we consider the times that the nearby times that have the similar representation, and times that far away from, such as far away from the previous times as we need to we restrict it to have a much larger distance.
Okay, I see.
And for example, for the ICE WS14 and 18 and data sets, you have daily granularity, right? One time step is 1 day.
Uh, one day construct a temporal
Okay.
snapshot.
I see.
Oh, okay. There is something wrong for the GDAL. Actually, it is 15 minutes. The gradually is 15 minutes. The GDAL is 15 minutes. It's not the daily.
There are also data sets called Yagu and Wiki. Did you also try your method for those data sets?
In this work, we do not try these data sets, but as for the Yago and Wiki, I found some features of this dataset, such as the Yago or Wiki. Nearly 95% of the facts are repeated every day. So we can regard it as a static knowledge graph. It's okay. So it has some differences from this ICWS14 and GDL, these data sets. So we do not conduct the experiments in this work.
Yes, makes sense. Thank you.
But in many, such as the temporal knowledge graph reasoning work in the exploration settings, they also conduct the experiments in the Yago or Wiki.
Are there any tricks to training this? For example, do you have to do like one of the other non-temporal methods to get the semantic embeddings first to warm start it or something, or do you just train everything from random initialization and it has no issue?
I think the trick is we need to make the timestamps nearby in the nearby timestamp have the similar representation, and then such as another trick is that so okay, that's all.
So how do you get them nearby time steps to be close in space? Is that an initialization thing, or is there some pre-training step that enforces that?
We have no pre-training on this, but the two operation make the nearby times that have the similar representation. The first is the shell time window, because we can set the time windows such as 3 days share the same embeddings. So we can make this representation in the same time window have the similar representation. And the second operation is the timestamp regularization. So the two operation can make the chaining process lead the chaining of the timestamp embeddings have the phenomena that nearby timestamp shall have the similar representation.
Thank you.
So if there are no more questions, I think we can wrap up here. And thanks again for presenting your work and share the insights with the group. And we will see everyone hopefully next week.
Okay. If you have any questions, you can email me